So our next speaker is Yang Huang from NTU, National Tsing Hua University of Taiwan.
Yeah.
And they are here. Would you mind sharing your slides?
Okay. Can you see my slide?
Yes.
Okay. And hi, I'm Yang Huang. And before start, I want to let you know that because English is not my native language, so if there is any unclear in my presentation, please feel free to interrupt me. Okay. Yeah. And I'm honored to present our study on mitigated bias in MRI-based Alzheimer's disease classifiers through pruning of deep neural networks. And this work is done by myself, National Tsing Hua, and Zhao Shenli, and our advisor, Guo. And we all come from National Tsing Hua University in Hsinchu, Taiwan. Okay, and first, I would like to quickly go through the bias in medical deep learning models. And first is training data bias. It arises when the training data used to develop this model does not truly represent the diverse patient population it aims to serve. And the second factor would be sampling bias. And the method used to collect data can introduce bias if they are not designed to capture the full medical conditions. And third factor is data preprocessing bias. If the data preprocessing methods such as data cleaning and feature selection are not used properly, it may introduce or reinforce existing bias in the model. And the fourth factor is evaluation bias. It arises during the model assessment phase. If models are not properly tested, the bias may not be apparent. And to mitigate bias in ML models, various methods have been proposed, including adversarial learning, perturbation of loss function, data preprocessing, and training of multi-sources datasets. The first one is adversarial learning. This is a technique that involves training a model to not only make prediction, but also defend against features that induce bias. And the next is perturbation of loss function. It involves modifying the loss function to account for fairness and equal treatment. And the third one is data preprocessing techniques such as oversampling or reweighting, which aims to balance the data to reduce bias. And the last one is training data on training data that combines data from various sources can help ensure that the model is trained on a diverse set of patient data. And now the research has explored the potential of using machine learning models on MRI data for the diagnosis of Alzheimer's. And like using a stacked autoencoder to learn hidden representation, followed by a softmax output layer, or using contrast-free learning with metadata that improves the pre-training efficiency and improves the performance after fine-tuning. And even adapting feature learning by playing the Rubik's Cube, which enforces the models to learn invariant features from 3D data and boost the accuracy of the 3D deep learning model. Okay. And our research focuses on mitigating bias in deep learning models used for Alzheimer's disease diagnosis with brain MRI data. we aim to reduce bias induced by age and gender. And the method we use is model pruning. And we hope to reduce the bias without compromising the model's performance. And our study used the T1 weighted structural MRI dataset from the EDNI database. And the dataset is summarized in the table. And after we train a baseline model, which didn't go through any debiasing technique, and we conduct t-test, and the results show that there are disparities in the model. For the gender attribute, p-values for being biased across age groups are across age groups are 0.002 in AUC and 0.03 in TPR. And the p-values for being biased across gender groups is 0.02 in accuracy and 0.2 in precision. And while the pruning method is powerful, there are some limitations. Here is the pruning method proposed by Moskin-Fix, and the overall pruning process is done by validation set. The process is demonstrated in the figure. And first, we will choose a layer in the pre-trained model to be pruned. And next, we will calculate the bias influence of each node in the model. As for the calculation, it can be done by equal opportunity difference, BOD, or statistic parity difference, SPD. BOD represents discrepancy between the TPRs of the model, and SPD is defined as difference between the probabilities of positive outcomes. And once the bias values have been calculated of each node, and we will then sort the values and prune the node with higher value. And in the following step, we will reassess the bias in the model and the model's performance, and check whether the model's performance dropped below the threshold or the bias reached zero. If it does, the process will end. If it does not, then we will repeat the process. And after the pruning process, we will get a pruned model that is debiased. In our extension, we propose three modifications to the pruning algorithm to enhance the method efficiency in mitigating bias while maintaining model's performance. The first one is considering performance influence throughout the pruning process. To avoid removing the important nodes which are crucial to the model's performance, we also calculate each node's impact on the model's performance. And by calculate the difference of the bias influence and performance influence, we can make sure that we remove the bias nodes while maintains model's performance. And the second adjustment is enabling continuous pruning even when bias reach zero. Given that the dataset may be small, if we stop pruning once the bias reach zero, the pruned model may not be fully debiased. Therefore, we adopted a more resilient approach that continued the pruning process even when the bias reached zero. As a result, the bias values are allowed to fluctuate in proximity to zero, ensuring a more comprehensive debiasing of the model. And the last adjustment is incorporating TNR information into the bias evaluation metric. Cause the function EOD focus on TPR disparity during pruning, which may not achieve for debiasing. So we introduce balanced accuracy BA and balanced accuracy disparity, and which represent the average of TPR and TNR. Yeah, and above are the three adjustments we proposed. And next, I will demonstrate our experiment results. We conducted our experiment by fivefold cross validation, and to assess the model's performance, we utilize various metrics, including accuracy, AUC, precision, TPR, TNR, and equalized odds. And the lower equalized odds indicates that equally high performance of each group. And to further test our method, we also conduct different debiasing methods on the same dataset. We have conducted 5 kinds of debiasing methods, including adversarial learning and adjusting loss function to penalize the maximum mean discrepancy distance, and adjusting loss function to penalize the mean distribution across each subgroup, and training the model on a balanced dataset by upsampling with and without data augmentation. And the figure demonstrate this figure demonstrates the comparison of the overall model's performance. And the models were debiased using age information, which is the left part, and debiased with gender information, which is the right part. And each line represents a result of cross-validation, and the solid dot means the mean value of fivefold, and the red dot correspond to the male or younger subgroup, while the blue dot correspond to the female or elderly subgroup. And we can see that the black line is our pruning result, compared with green line, which is the baseline. Our proposed method maintain or even improve the model's performance across various metrics. Okay. And the next figure demonstrates the comparison of the model's performance disparities. The disparities was measured. Sorry, is there any question?
You have about 1 minute left. Thank you.
Oh, sorry. And the disparity was measured by taking the absolute difference between the subgroup, and in this context, the lower values indicate a more fair and more equitable outcome. Yeah, and left part is about age, and the right part is about gender. And we can see that our proposed method mitigate this disparity for multiple metrics. And about last experiment, we compare our approach and the original pruning method with and without 3 adjustments. We can see that after the 3 adjustments, the pruning method was more effective. And the last is discussion. Our current pruning method focus on binary classifiers, but how to address the interaction among multiple classes? And the next is our method application across diverse demographic distribution needs to be tested. Yeah, and that's all about our study. Is there any question?
Thank you very much for the nice study. I have collected some questions, at least from the panelists.
Okay.
Could you please comment on the difference between either performing or training a low capacity model in the first place versus, as you do, training a high capacity model and then pruning it to achieve a lower capacity? What is your experience in the difference between those two approaches?
You mean the original pruning method compared with our proposed method?
No, so when you prune, you essentially lower the number of parameters in your model, right? And you could train a model from scratch that didn't have that many parameters. So do you observe any differences in performance between these two approaches?
No.
I mean, is there an advantage to first training a higher capacity model with many parameters and then pruning it, as opposed to just having a lower capacity model in the first place?
Our method is set the output of the prune node to 0, so the capacity is same. So there will be no difference of the number of nodes in the model before and after the method.
Okay. Another question. So here you look at disparities in the correctness metrics or in fairness metrics across age, but you also know that Alzheimer's disease diagnosis themselves have a bias across different age groups. Is this a problem?
Can you say that again?
So here you show that the diagnosed, or you show that your different performance metric are different across different age groups, and that includes also the fairness performance metrics.
Yes.
But we also know that the diagnoses themselves are biased by the age group. Could that be one of the reasons why you observe a bias in the first place? And if yes, is it a problem?
Yes, because maybe the elderly group can be observe the Alzheimer disease more easier. So yeah, that may be a problem. Yeah.
Is there a way to take this into account?
Take into account. I have to think a while.
It's completely
our ideal model can tell the difference between the Alzheimer disease and normal people. So it's ideal so no matter the age of the people, we hope to have same performance of each group. Yeah, so we try to achieve this by device.
All right. Thank you very much for your talk. Thank you again.